Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 54. Now, today we are going to discuss about the how I can solve the structural problem using the finite element. Okay. Though the finite element is a very vast subject and we cannot cover the entire thing. So, but the thing is required for to proceed and to solve this hydroelasticity problem, that part we are going to definitely discuss today. And this is the keyword that you have to use to get this lecture. Okay. So, let us start. Now, we are going to use this Euler beam theory and this equation is 1.12, just if you remember this connecting to the previous equation, this it is actually the beam equation that we are going to solve. Now, here if you look at this equation 1.12, this term the buoyancy term actually we can take in the right hand side. Okay. So, therefore, I mean if you do that, then I just cross this thing and simply I can write this term equal to the f x t. Okay. Because I am taking this term in the external force, because this is coming because of the buoyancy force. Okay. And therefore, since it is a free beam, you can assume that a ship, you can consider the ship is a free beam which is resting on a spring, one can say like this buoyancy force can act as a spring. So, therefore, the shear force and the bending moment at the both the end is going to be 0. So, this is the differential equation that we are going to solve and with respect to this boundary condition. Now, how I can solve this differential equation? So, there are so many ways you can do that. You can convert this partial differential equation. You can see here this w is the both the function of space, that means x, as well as the time t. So, the basic idea is convert this equation, the partial differential equation, into the ordinary differential equation in terms of t. Now, there are many ways of doing it. The popular way of doing is that we can use the separation of variable, like for example, you can simply take this w x t equal to some function of x and then some function of t, and then you can substitute the whole thing here, you can solve this problem. Remember, this right hand side also we need to see how we can convert this function only in the function of time t. So, this is one way. So, there are many ways you can do. Actually, popularly you can say there is a two, you can call the strong way I can solve the problem, or sometime you can say I can solve in a weak form. Okay. So, now let us see that what is the difference between a strong form solution and the weak form solution. Now, in strong form solution, that the solution you are taking as it is, like you are not making any changes to the differential equation, and also the solution of this problem entirely that satisfy the requirement, the differentiability requirement or continuity requirement, everything. For an example, like the classical problem of string, let us take a second ordinary differential equation, which is let us say d square y by dt square plus let us take k into t k into y equal, let us take it is 0, let us say. Now, I try to solve. Now, you know that this the solution is it is some sin equal, let us say k square. So, sin k t plus a 2 into cos k t. So, this is the solution for this particular problem. Now, here one can say this continuity, differentiability, everything is preserved over here. Now, if you look at a string, now this string actually realistic way I can see that it can I can see this as my approximate solution. Now, if you look at the sin k t or cos k t, so you can see the actual the solution is in this form, right. It satisfies all the condition. Now, it is a strong form solution. Now, suppose I assume my if it is a string, so it is just connected here, and then if I assume that string can actually oscillate in this fashion. Now, here it is a second order differential equation, but however, I can see it is a realistic solution, but here I can see that the second order differentiability is not actually maintained, is it not. So, physically I can see that that could be a solution, right. If you take a string and then if you oscillate it, it more likely it is going to look like this way, right. So, let me just rub it and draw it somewhere here. Yeah. So, the same picture let me draw over here. Now, in realistically, if you think that this is a approximate solution of the string problem, so one can say it is valid. I mean it is practical, but it does not maintain the all this differentiability requirement. So, it does not. So, in weak form solution we can approximate some solution, but that does not maintain all the differentiability requirement of the solution, right. So, in one way the all strong form solution can be a weak form solution, but all the weak form solution cannot be a strong form solution. Okay. Now, let us see like some analogy, like how we can see the solutions. Like now, suppose one can see like the v equal to 0, like say a vector v, that vector v equal to 0, okay, fine. Now, alternatively what I could say is like that a vector like let us assume that how I define a 0 vector in alternative way. I can say that suppose G is become any vector apart from the 0 vector, any vector in a 3 dimensional space or n dimensional space. Now, here at this point I really do not want to confuse you with some space problem in n dimensional or whatever, but you considered a 3 dimensional vector space. So, you have the component x and y and z. Okay. So, then I assume this a G vector is something like this, and then for all G belongs to this space, let us say this vector space S, that V dot G, this dot product should be equal to 0. So, it means that this vector V is orthogonal to any of the vector in the vector space. Then I can call this V is a 0 vector. See, idea is very simple. Idea is, so to tell something equal to 0, I just coming with some condition. Now, I say simple V equal to 0, I can see it is a 0 vector, but I am not saying that is a 0 vector. What I am saying that I collect all the vector G which belongs to this 3 dimensional space. So, G is the collection of all vector, any vector that belong to this space, that vector space. Now, if it is so, then V, the dot product of V with that G is always equal to 0. That means that V is a orthogonal to the all the vectors in that vector space. It means V is a 0 vector, right, because it is not possible that you cannot find a vector V apart from 0 vector. If you take a dot product with any other vector, it becomes a 0. Think like if I take V equal to some vector x I plus y j plus z k. Now, if you take any arbitrary G vector which is maybe that G vector may be equal to G I, G 1 I plus G 2 j plus G 3 k. So, then dot product is x G 1 plus y G 2 plus z G 3 equal to 0. Now, if these two are independent or whatever, this is only possibility that x, y, z should be equal to 0. Otherwise, otherwise it cannot be 0. Okay, so, this is one way I can say that V equal to 0 directly I say V is a 0 vector. Alternatively, I can make another comment that a vector which is orthogonal to all the vectors are called the 0 vector. Now, let us see how I use this idea for this the finite element thing. Now, if you take this differential equation over here, so I can write this equation in little bit composed way Lu minus mu equal to 0. Now, here this Lu minus mu equal to 0, see one is saying this equal to 0, right. This is the normal way one could tell. Now, let us consider this as a infinite dimensional space. Now, again I am not want to confuse you as the infinite dimensional space and all, but let us solve this problem in some numerical or approximate way. So, I assume that u equal to u bar is the approximate solution. Now, approximate solution cannot be equal to the main solution. So, therefore, there must be some error and I can define this error as E. Now, how the previous idea helps over here, I assume that this error E should be a 0 vector. Now, I assume this G, the vector, any vector G or any function G which is the which belongs to the solution space. Now, this G could be the strong form solution. Okay. Now, if G is belongs to the solution space, then it should be orthogonal this to the error. So, the idea is I am simply telling that this error, now if it is really a vectorial operation, I could say that error dot G that should be equal to 0 if it is a vector, but it is not, it is a function. So, I am using this symbol defines that. Now, this E dot G means that E and G are orthogonal to each other, normal to each other. So, I can say that this error is orthogonal to the vector G. It means that this error does not belong to the space. Now, this is the basic key aspect of the finite element. I approximate a solution u, I try to calculate the error and then I multiply with some function g, we call this function as a test function, and this test function definitely be the solution of the problem, and therefore, this should be orthogonal to the error function. So, this is how actually we approach for the finite element, and that is the basic of the finite element. It is a very vast and therefore, a lot of theories and lot of things are available. So, I am not going to go into deep into that. So, with this let us try to figure out how I can solve this structural problem. Okay. Now, here now this is something that solution space you can say, like you call a test function. So, test function could be anything like this, right, because you can say it is a mode. Okay. So, if a thing oscillate, as I said that this weak solution may be some realistic. Now, if you think of a flexible structure, it can oscillate in any it could oscillate like this way, it can oscillate like this way or this way, it could bend like this. So, the all could be the possible solution. Anyway, so let us now start that how actually I could solve this problem. Okay. So, now remember that I put that stiffener part in the right hand side under the fxt. So, if I do that, so I left with this following thing, which is m into del square w by del t square plus del x square E into I del square w by del x square, this equals to f x. So, I can call this is equals to f x. So, now what I can do is I can make in the left hand side. So, I write it is minus of f x equal to 0. So, now I can approach that a approximate solution of W, and then I have to use some test function which actually is the solution of this space, and then it should be orthogonal to the each other, right. So, now how I can set it? So, I can find out my error function, you can say here E x, let us say it should be m into del square W by del t square plus del square del x square into E into I into del square W by del x square and minus f of x. So, now I have to define some test function v, right. This test function v with this error function E x, it should hold some orthogonality property that should be equal to 0. So, this is my idea. Now, how I define this? I define this way. If I integrate 0 to L, then this v comma E x, this error, and that should be equal to 0. So, this is my orthogonality condition. Now, it is bit mathematical. So, but the application is pretty easy. So, it means that what I try to say, I just multiply 0 to L this integration. So, I integration the whole error function. So, which is m into del square W by del t square plus del square by del x square into E into I into del square W by del x square minus f of x. So, this is the whole thing. I multiply with this function V x or function of x and t. So, V, and then the whole thing, if I integrate along the length x, that should be equal to 0. So, this is the basic idea of the whole thing. Okay. So, now in next step what I am going to do is I am going to simplify the thing. Okay. So, in next I am going to simplify the thing. So, let me do that. So, 0 to L, and then I just now if you remember see this the last term. So, the first this V should multiply with this term. So, it is a function of t. Okay. So, then just write it out m into V, and then it is del square W by del t square into dx. See, this is the term actually I am separate out, and then I am doing this next part. So, I just split again, it is 0 to L. Now, this V should be multiplied with E into I into del square W by del x square, right. I think this is it, yes, and then multiplied by the dx, and then minus 0 to L f into V into dx, that should be equal to 0, right. So, I am not doing anything with this. So, I am just using try to solve this by integration by parts. So, I am writing it is as it is 0 to L into m into V into del square W by del t square into dx. Now, if I do integration by parts, so I will get V into E I just a second. Oh, sorry, I missed this part, that is what I am thinking. So, I just missed this part here, del square by del x square into V, yes. So, then it should be, now it is V multiply the integration of this. So, it should be del x into E I into del square W by del x square, you put 0 to L, and then integration by parts. So, therefore, it is 0 to L. Now, differentiation of V is del V del x, and then integration of this part. So, it is del x into E I into del square W by del x square into dx. Now, why it is? Because you see it is integration. So, it is del square by del x square. So, that is why it becomes del x, right, because of the integration, and then minus it is 0 to L f into V into dx. Now, if you apply the boundary condition, the shear force, so del square by del x, it is 0 at both the end L as well as the 0. So, this goes to 0. So, I left to it 0 to L m into V del square W by del t square into dx. So, this is the first term, and then I have this one. Now, again if you do integration by parts, then you will get minus it is del V del x and integration of the second part, which is E I into del square W by del x square, it is 0 to L, and then again plus. Now, it is the differentiation. So, it is 0 to L del square V by del x square, and then it is integration. So, it is E I into del square W by del x square into dx, and then it is finally minus 0 to L f into V into dx, that should be equal to 0. Now, again if I apply the boundary condition, so this goes to 0, right. Now, if this goes to 0, then finally you have 0 to L, it is m into V del square W by del t square into dx, and then this goes to 0. So, this term, so plus 0 to L and del square V by del x square, then E I del square W by del x square into dx, yeah, and minus 0 to L f into V into dx, that should be equal to 0. Now, this is the final formulation. So, now we have to find out the value for this, and now this finite element concept we can use. Now, what I do is, now if we assume this is a beam element, so I can similar to the panel. Now, you know the panel method. So, you do not have difficulty to understanding this. So, assume these are the elements, this could be the element number 1, this could be element number 2, assume that there is a element number E. Now, if you take this element E, okay, then I can allow is a 2 degrees of freedom. One is you can say here I can say it is a W 1. So, it is a displacement, and also I can call the slope dw by dx at 1, and then I have another element here, you can call this a W 2 the node, and also I can call this dw by dx at 2. Okay, so, I have a 4 degrees of freedom, right. Now, if I have a 4 degrees of freedom, that means I have 4 unknown, is it not? Now, this is one, that then how I can write that now still now I did not write the approximate solution. So, how I can approximate the W? Now, since I have the 4 unknown W 1, W 2, so I need 4 equations, right. So, therefore, the function actually I need to write the approximate function, it should have the 4 unknown. So, therefore, it should be cubic polynomial, right. So, I just write this is in terms of a 0 plus a 1 into x bar. Now, this x bar is the approximate solution, and then a 2 into x bar square plus a 3 into x bar cube. Now, similarly, I can write this another function also V x. Remember, I am just not writing the t term, though it is there. Now, V x equal to, again it is you can call B 0 plus, because I am integrating along the lengths, right. So, it is B x bar B 1 x bar plus B 2 x bar square plus B 3 into x bar cube. Okay. So, now thing is that I have this 4. So, now let me just very quickly just say that I can express, like if I put 0 over here. So, here 0, if I put x bar equal to 0. So, I can use it A 0 is equals to W 1, right, W 1. So, and then you can say similarly, if I differentiate this with respect to x. So, I know that my A 1 should be equal to del W 1 by del x, or you can say del W 1 by del x 1 at W equal to 0. So, W 1 it is W 0 this way, right. And then if I take this now, if the length I assume this length of this element is L e. So, similarly I can write that the other condition also I can write, it is W 2 L e or W 1 L e equal to A naught plus A 1 L e plus A 2 L e square plus A 3 into L e cube, right. And then I can write for the del W by del x at, now at L e it is 0.2. So, it is 2 over here and it is L e. So, it should be A 1 plus 2 A 2 into L e plus 3 A 3 into L e square, right. Fine. Now, you see now from here actually what you need to do is you need to write the expression W x not in terms of A 0, A 1, A 2 and A 3. You need to write the whole expression in terms of W 1 0 and del x del W del x 1 at element 1 0, then W 2 L e and del W and del x 2 at L e. So, this is how actually you need to write the whole expression. Okay. Now, this is actually very much possible. You need to do little bit exercise and then you can find out that normally if you do this exercise. So, I can just say that how it should look like. So, this W x bar it should look like some W 1 e with multiplying with some function n x plus del W by del x at 1 into n 2 x plus W 2 e into some n 3 x plus sorry, it is del W by del x at node 2 this element at for element t into n 4 into x. Now, this is actually you should try a little bit and you can write this, you can eliminate this A 0, A 1, A 2 and A 3 in terms of this W 1 and then del W del x 1. Okay, I forgot this element t, for element t of course, W t and del x del W del x for the second node for the element t with respect to this. And this n 1 n 2 n 3, this is called something called the shape function. This is something called the shape function, okay. And people and sometimes call it a Hermite polynomial as well, okay. And similarly, I can write for the Vx also. Vx also I can write in this form. We can this V1 e into n1 x plus del v by del x for element 1, I mean for the node 1 element t, which is then n 2 x plus V 2 for element t into n 3 x plus del v by del x for element t, the second node, into n 4 x. So, now this is how actually I write the approximate solution. Now, let us see that how actually if I solve this, if you solve this the whole exercise. So, you can get these shape functions, this n 1, n 2, n 3, n 4. Now, this xi is nothing but the approximate, which I called as x bar. So, so here it is written as in xi form, but anyway. So, this okay, this bracket is missing over here, yeah. So, now if you do this, then actually you get this solution n 1, n 2, n 3 and n 4. Now, this is how actually this shape function. Now, you see the important something is very important over here. You can see that if you look at the node 1, okay, only you can see that only the shape function 1 actually is 1 and remaining values are 0. So, therefore, in element 1 you can see that the deflection has the maximum impact, right. Now, similarly, you can see that this n 3, it is 0 over here when xi equal to 0, and then it is here when xi equal to L e. Now, if I look at this n 3, then you can see that for this beam, and here actually that this n 3 has the maximum impact and remaining terms are 0. All other terms are, you can see that it has no effect, the slope has no effect in the both the end, right, the slope are 0. So, and also here you can see that here also the slopes are 0, which satisfy your shear force and bending moment, right. So, anyway, so let us stop here. Now, what we stop here, that where I can write the approximate solution in terms of the shape function and the nodal variable, which is W 1, del W del x, W 2 and del W del x at node 2. Now, in the next class we will try to figure out that how this will helps me to solve the structural problem. From here, how I can write the element matrix and then how I can write the global matrix and how I can solve, all these things we are going to discuss in the next class. Okay? Thank you.